My name is Magnus Ahlgren, and I'm from Chalmers University of Technology in Sweden. So I will present some work that I did together with my PhD student, Wissam Aoudi, also from Chalmers, and Miquel Iturbe from Mondragon University in Spain. So the idea was that Wissam would present this talk as the first author, but unfortunately he didn't get the visa in time, so I'm the stand-in. And Miquel is also here to help me with the questions towards the end of the talk. So in this particular paper, we looked at industrial control systems. So these are systems that control industrial processes. And you can find them in very different types of scenarios in society. You know, the smart grid, manufacturing, production, and so on. And many times they operate on critical infrastructures. What we've also seen is that attacks against these systems are increasing. So sometimes when we speak to stakeholders, they tell us about the attacks, but we can also read about them in the news. So one of the recent famous examples would be the blackouts in Ukraine. So 2 years in a row, we had blackouts. And these types of attacks can be quite good for the attacker because they can have dire consequences for society. So in Ukraine, they cut the power when it was pretty cold outside. And you can think about worse scenarios than that. So in industrial control systems, you have a process. So the process is really in focus, which means that some of the classical mechanisms we have from IT security do not fit well. So we need complementary techniques, a little bit of a defense-in-depth thought here. So we look at process level attack detection. So why? Because the industrial control systems really combine IT with operational technology. What we do, we look at the physical process and see if it deviates from the norm. And we do that by monitoring values from the system continuously in real time. So here you see a control loop, very similar to the last talk here. So in the center of the system, we have a process. We have sensors that monitors the process, sends the value to a controller. The controller has decision logic to send commands to the actuators to make sure that the process behaves according to specification. So in the paper, we consider an adversary that could compromise sensors or maybe compromise the communication link between the sensors and the controller. The adversary could also compromise the communication link between the controller and the actuators, or possibly also the controller as a whole. So ICS systems are deterministic. So the controllers, or the PLCs, programmable logic controllers, many times behave in a cyclic fashion. So that means that the signal repeats, and in many of these systems, there is high level of determinism. And this allows us to use, to learn the normal behavior or to model it in a good way. And this is key to our method that will come after. So the regularity of the ICS behavior really allows the data-driven approaches where you can learn directly from the data from the system. So if we look a little bit at existing methodology, there was actually a paper here at CCS 2 years ago that had a good survey and also talked about very stealthy attacks against industrial control systems. So the idea in many of these systems is that you start to build a model of the physical process. This can be quite intense and quite difficult. You need experts to define this model. Then you use this model to predict future system behavior. Then you look at what you actually get from the system. You calculate the residual, and if it's large enough, you would raise an alarm. So one of the problems here is really that they solve a more difficult problem, a more general problem than it's needed. So they try to predict the future, and then they use these predicted future values to see if the system really behaves as it should. And this is difficult. And predicting the future introduces some noise in the whole system. So in PASAD that we show in the paper, it's a process-aware stealthy attack detection. We have a number of contributions, and I'm going to mention 3 of them. So first, we solve an easier problem, and I will talk a little bit what I mean with that just in a slide. PASAD also requires limited knowledge on the system dynamics, and it's capable of detecting subtle attacks, so the attacker have a harder time hiding within the noise levels. So why an easier problem? So we learn from the normal behavior based on historical data. And then we collect values in present time, so we never jump to the future to see if they conform with the estimated behavior. So in PASAD, there is no need to predict the future, and we avoid some of the noise that would come with such a step. PASAD also required limited knowledge of the system dynamic. We tried to really build an entirely data-driven system. So we use the raw sensor values from the system. We don't create system-specific features, but really try to use the raw values so it would work on a number of systems, and it's model-free. And in the validation, we've shown that it's specification agnostic. So we tried it on a number of different systems, and it works quite well, regardless if it's a paper mill or a water distribution plant or a simulation of a chemical factory. So PASAD is also capable of detecting subtle changes in system behavior. So here I jump forward a little bit and talk about some of the validation. So in the validation, we use the Tennessee-Eastman process. So this is a simulation of a chemical plant. And as part of the paper, we have defined a number of attacks in this setting. So some of the attacks are very obvious. The goal of the attacker would be to destroy the process and make sure that the chemical plant stops. And you can see the behavior here, that it's very easy to see that something strange is happening. But we also introduce a number of stealthy attacks, where the goal of the attacker is to change the process just slightly so they can hide in the noise, but still influence the process over time. Maybe as a competitor that would make the process less profitable to run. So these attacks we also release with a paper, so other people can use the attack data to compare with our system and make improvements. So PASAD, as I will show, is really capable of detecting these strategic adversaries that hide within the noise. So what do we do? I will give you a short overview of the steps, then go a little bit deeper into the math, and then I will show you an example to kind of go through a setting, how you would run PASAD in a real-life setting. So we have two phases. One is an offline training phase, and the second one is online detection. The offline training phase is a little bit more computational expensive, while the online phase was designed to be able to run on systems that you would find in industrial control systems. So with not so many, where they might be computational restricted. So it can run on relatively simple hardware. So in the learning phase, we try to create a mathematical representation of the norm. We extract signals from the system, we remove the noise, we construct something we call the signal subspace, and we project a number of training vectors onto this space. And then we compute a centroid, which defines the normal behavior. In the detection phase, we track the distance of new values that the system emits and see how large, how much they deviate from the normal space. So we project these vectors onto the same signal subspace, calculate the distance, and if it's larger than a threshold, we give an alert. So more in detail, you would start with a time series. And again, we try to work really with the raw data from the sensor, so nothing system specific, so it would be applicable to a number of systems. We embed it in a matrix, and this matrix has a number of mathematical properties that we describe in the paper, but I'm not going to talk about it here. We then calculate the singular value decomposition. We get the number of eigenvectors. We choose some of these to remove the noise, and then we let these define the signal subspace. We project the training vectors onto the signal subspace and compute a centroid to define the normal behavior. Then in the detection phase, we continuously collect new data, and for every new test vector, we project it into the signal subspace and calculate the departure score. And if this score is large enough, we're going to raise an alarm. So in the paper, we also have 2 more features of the system. I'm just going to tell why we have them and not so much the math behind them in this talk. So again, go to the paper for the interesting stuff. So the first is an isometry trick. So we show that we don't need to use the full projection matrix. We can actually use something simpler to make sure that it can run on hardware that you would find in industrial control systems. So it becomes faster with less need of expensive hardware. And we also show that the signal subspace is isometric to Rn. And that means that we can visually show how the system works to kind of create an intuitive feel for the steps and what they happen. So that second one is what I will show you now. So you see a little bit how the system would work. So up here, you have the signal from the system. This is the same type of subtle attack from the chemical plant that I already talked about. Down here, you have the calculation of the departure score with a threshold defined. So if anything goes over this threshold, we should raise an alarm. And over here, we have the signal subspace where we visualize what happens as the system goes on. So you get a feeling for what it is about. So in the training phase, we collect training vectors. We learn from the historical data. So again, we never jump to the future. We're always working in the present time. These vectors form a cluster in the signal subspace. We use that to calculate the centroid. And then in the testing phase, so in the online detection, we collect continuously the values from the system. We project them on the signal subspace. As long as the system behaves normally, it will fall very close to the already collected data. And the departure score is not so high. And then we introduce an attack. And then immediately we can see that the vectors will depart in the signal subspace from what we define as the system behavior. And the departure score will increase quite drastically. And as the attack is ongoing, the system shifts. So even if you don't see so much from the actual time series, we can notice the difference quite noticeably in the signal subspace and with the departure score. So PASAD was tested in a number of different scenarios. So the first one was the Tennessee Eastman process. So this was a simulation of a chemical plant. And as I said, we also created a number of attacks in the paper. And the data from these attacks we're releasing with the paper. So you can try with very obvious attacks where the process is stopped towards stealthy attacks where the system keeps on running, but maybe not in an optimal fashion. We also use the SWOT dataset. So this is a dataset created by the iTrust Institute. So they have a large testbed. So they have a dataset where they run the system, and then they interject a number of attacks that they have created into this test dataset. We also took PASAD and let it run on data that we collected from a water distribution plant in Gothenburg for about 3 months to see how it would behave in a normal setting with real, very noisy data. So very short, some of the results. Here on the right-hand side, you have the Tennessee Eastman results. So in the beginning, PASAD would learn the behavior, then we would run it, and towards then you would detect the attack. So in the first case here, the attack is quite obvious, and it's quickly detected. In the second case, the attack is a little bit more stealthy, more difficult to detect, but PASAD still detects it. Up here, you have the data from the water distribution plant in Gothenburg. And down here, you have the SWOT data sets. So the normal behavior is the black bars. And then at the number of points, they've inserted the attacks that change the behavior. We also made a comparison with a previous method in the literature that's also data-driven. So this is an auto-regression method. So the idea between this method is that they take historical values and they try to predict the next value. And then they observe what the system will emit and make a comparison between the predicted value and what the system emits. So we ran PASAD and the autocorrelation on the same data. And you can see the result here. The first example is quite, again, a very abrupt attack. It's very obvious that something happens to the signal. So depending on the method, we have two different thresholds. So the blue line is for PASAD down here, and the black line here is for the autocorrelation to make sure that we do not have any false alarms during the normal operation. So in this particular case, both systems can detect the attack. PASAD detects it a little bit before the autocorrelation system. In the second example, the attack is much more stealthy. So the changes are not so visible. And in this particular case, PASAD can detect the attack, but the autocorrelation method can never detect it because it's difficult to predict the future. And the attacker can hide in this particular case. We also took PASAD and put it on an embedded system and implanted it into a real environment for 75 days to see how it would behave, check system performance, and so on. So it was running in a paper mill north of Gothenburg for 75 days. It sniffed the network packets, analyzed them, and told us about the system behavior. And it ran without any technical issues encountered. So to summarize, we can see that attacks against industrial control systems are increasing. Process-level attack detection is complementary to many of the classical IT security mechanisms that we have. And it's important in these systems to have defense in depth. Many of the existing methods solve a much more general problem. And sometimes when you try to detect attacks, that penalizes them because the attacker can hide within the noise. So with PASAD, it's model-free. We try to design it so no features. We use the values directly from the systems. We have a sound theoretical basis. It's specification agnostic. So in the paper, we tried it on 3-4 different systems, and it worked quite well, even though they were quite of different nature, from water distribution to chemical plant to paper mill factory. We also designed the online detection to be lightweight, so we could run it on resource-constrained hardware. And since it's noise tolerant, we can also detect attacks that are quite subtle in nature. So with that, I conclude this talk and let you ask questions.
Hi, Magnus. Avais Rashid from University of Bristol. Great talk. I was just curious, can you say a little bit more about the more complex attacks that you mentioned? So when they're stealthy, are they, for example, value tampering attacks? Are they sensor spoofing? Are they hiding in the safety margins? To what complexity do you get in terms of those attacks?
So Mikael was the one who created all the attacks, so I let him take the question. Okay. So you get, please.
Yeah, sure. In this case, the first type of attacks were that it didn't reach the safety limits. So that was the first thing. But next, we created some attacks that did not hinder process operations so much, but they did have an economical impact. They were both types, both tampering with sensor values, so we could trick the controller to take the wrong decisions, and also just tampering directly the actuator value so we could play it. In this case, the stealthy attacks were designed to make plant operation more expensive just by increasing the operating cost, but also decreasing the quality of the final produced product.
Okay, just a quick clarifying question. So at any point, do you consider that the sensor itself may have been compromised, or do you take the sensor as the ground truth value, that what you're getting from the sensor is always going to be correct?
In this case, we consider the sensor value to be the ground truth. There are other works in the literature who ensure that the veracity of the sensor value is good. We consider this work to be complementary in that sense.
Okay, thank you.
Hi, nice talk. Was wondering though, since you're training based upon normal behavior, couldn't an attacker evade the system by just waiting till an unusual event such as a lightning strike upon the plant to do their malicious attack?
Possibly. That's something we haven't tested, but so sometimes in this system we also get alerts that are not attacks, but related to very anomalous behavior of the system. And it depends on if the attacker would take advantage of such an event. It's possible that also the system engineers would kind of restore the plant afterwards. So it's a question how useful that would be.
Okay. And the flip side is, if an unusual event does happen, could your system think that it's under attack and therefore impede recovery from the event?
So in this particular case, sometimes when I give this talk to stakeholders, they like more that it can detect unusual events over attacks, because they see many more of the unusual events, so they see that as a feature and not as a problem.
Okay.
Hi, Vishai Wall from Tel Aviv University. So it seems that what you've done assumes a homogeneous process. In that water treatment plant for 70-something days, it was doing the same thing effectively. So I'm wondering, we saw in data from a different water treatment plant doing something else, obviously, clear evidence of phases where the process would stop doing one thing and the signaling would start looking completely different for long periods of time. Did you see anything like that in your environment?
So we tried on different signals, and it also depends a little bit on the training period and how long you let it run. So when we went to the paper mill factory, we in the beginning assumed that we could manage with a shorter training period, and the system worked okay, but if we increased the training, it was much, much better. So this is a little bit a tunable parameter where you have to work to get the best results. If you have completely different phases and the system changes a lot, you lose a lot of the determinism, and then you would probably have different types of profiles. So we discussed that, but we haven't really implemented anything like that.
Thank you.
One quick question. Is the speaker of the next talk in the room? Yes, very good. Okay, just want to check. Okay. We can have one more last question.
Okay, thanks. James Landry, Lincoln Laboratory. Appreciated the talk very much. I especially like your willingness to go all the way with linear algebra. But I did have a question. One of the issues with not having a model is you don't have any intuition about how the system is performing or what it should be doing. How do you think this should be part of a defense in depth, and how would you combine intuition with the model so that you can have some idea of what kind of attack or what kind of problem is occurring? Because there's no actual information besides a general deviation from a threshold here, as far as I can tell. So have you thought about, deviating from the threshold in a specific direction might imply a specific kind of problem? How do you derive intuition about the situation? I like the visualization, but I'm trying to see how you get intuition about what's actually happening in the plant.
So the visualization right now is not so much for system engineer. It's more to get an understanding of the method and kind of see how it would work. You pose a great question. So we've also discussed with stakeholders with what to do with alerts. And it's difficult to find the right person in a company that would be able to understand enough IT security or cybersecurity attacks, and as well the process.
Right. So this pretty disjoint sets of knowledge.
Yes. So right now it helps because there is an alert and the company can put more people on the problem at that particular time. So they save money even though they might not know exactly from the system what type of attack it is right then.
So they're not really relying on any intuition. They're just like, something is wrong and we should start checking things.
Well, if I might add, those departure scores are related to a specific signal of the system. So
Right.
you know what signal is going wrong. So maybe it might be a pressure in the reactor, for instance. You might not know what caused it. You had to maybe look the logs or whatever, but you have kind of intuition where the problem is, not maybe what the problem is, but where it is.
Okay. Great. Thanks.
Okay, great. Let's thank the speaker.